All right. Well, happy Friday. It's week 8, Friday. Just a couple weeks left. I hope your projects are coming along well. Sign-ups are open, and I look forward to seeing your presentations. All right. Today I wanted to just talk about being able to kind of measure and look at relationships between numeric variables. And so the topic we're going to be looking at today is correlation. And we'll start off with simple linear regression. Now, this is an intro class. And so linear regression is a huge topic, and if you are a stats major or a data theory major, you're going to take an entire course on linear regression, multiple linear regression and things like that, and there's a lot of stuff that we can talk about, but here we'll just barely kind of scratch the surface. But I think it'll be useful for your projects. Certainly a lot of you will be looking at kind of, potential relationships between numeric variables, okay? So this is what we're looking at, right? Relationships between numeric variables. And so, for example, let's say we're looking at a housing data set for, a particular neighborhood. And what we see, we're going to see a trend. Let's say one of the variables we've measured, or variables in our data set, is the size of the house measured in square feet and its estimated value or estimated cost, okay? And what we'll see is this general trend. Houses with more square feet will have higher value. Houses with less square feet, smaller houses, will have lower value. That's not a surprise, okay? And we'd say, yeah, there is correlation between the size and price of a house. Let me just say something about the word correlation. Correlation, we throw that word around a lot. And in the context of statistics, it is reserved for looking at two numeric variables. Okay, correlation is reserved for looking at two numeric variables. So if you want to say, this categorical variable and this categorical variable are related, like if you are in category C, you're also more likely to be in category 3 or something like that. If somebody has diabetes, okay, which would be a categorical label, they're also more likely to have, high blood pressure or something like that, which is also a categorical label. It is in statistics, it is incorrect to say there's a correlation between having diabetes and having high blood pressure or something like that, okay? Correlation is reserved for numeric variables. We would not use it for categorical. You would say there's an association, or you would say having, one particular trait or category is associated with an increased incidence rate of the other trait or something. But we would not use the word correlation. Correlation is reserved for just kind of two numeric variables. If you wanted to say, okay, we're looking at blood pressure, the numeric value, and sodium intake, a numeric value, you could say there is correlation there because you have two numeric variables. But if it's categorical labels, we don't use the word correlation. Although, just kind of in daily language, correlation and association are kind of like interchangeable. But in the context of statistics, they have different things. Okay, but anyway, correlation, linear regression allow us to kind of quantify the relationship. Rather than just saying bigger houses cost more, smaller houses cost less, we can give it an actual quantity. And we can say an additional square foot in the size of the house corresponds to or is associated with an increase of $350 to the value of the house, right? So we have a quantity a way to kind of describe that relationship with numbers and quantities rather than just saying bigger X means bigger Y. Okay, here's a data set. This is from the Census Bureau. The Census Bureau has been kind of tracking marriage information. And so this is just everybody who filed for marriage. Not everybody, okay? They do a survey, so they don't actually look at all of the marriage records, but they do, they survey some information and to get an estimate. And the Census Bureau usually does a pretty good job of estimating these things. And here they're looking at, within a particular year, look at all the people who filed for marriage for the first time, right? So this is not second marriages or something like that. This is just people who are getting married for the first time, and how old is the person, okay? And they're looking at men and women. And so in 2019, the average age of men who are getting married for the first time in that year was 29.8 years, okay? And in 2019, women who were getting married for the first time, the average age was 28. This is not necessarily like this man got married to this woman, okay? It's not saying this person is getting married to this person, because you have same-sex marriage, and so, but it's like if two men are getting married and, one is 27 and one's 32 or whatever, it doesn't matter. It's just like, okay, who was a man who got married for the first time during the year 2019? What was their age? And, they kind of record that, and then they get the average, all right? And so this was, these are kind of the numbers, and so they've been tracking this since like, I guess 1890 or whatever. And if I plot men's average age of first marriage against women's average age of first marriage, what we see, this is kind of the relationship. Again, this is not saying like this man married this woman, because it's what we're saying is a relationship. Each dot is a different moment in time. And so I think 2019 would kind of correspond to over here, whereas like in this particular year, when men's average age of first marriage was something around 29.8, okay, women's average age of first marriage was around 28 years old, okay? And then there was another time where it was around, I guess, 27.8 or something like that, okay? There were, in the history of the United States or whatever, in the history of keeping track of this information, there was a time when the men's average age of first marriage was something around 23 years or 22 and a half years or something like that, okay? And during that time in history, okay, the average age for a first marriage for women was something around 20 years, okay? So this was a period, time period where people got married at a younger age, right? And there's been kind of times in between where average age of first marriage was, 26 or 27 or 28 or things like that for the men, and, some kind of thing. What we see is a very kind of a strong relationship in that when, in years where men's average age of first marriage was high, those also correspond to years when women's average age of first marriage is high. And in years where men's average age of first marriage is low, those also correspond to years where women's average age of first marriage is low. We don't really have any instances where men's average age was much higher and women's average age was much lower, or the reverse kind of thing. This is just kind of the trend that we see in the data here, right? And so we'd say, there's a strong relationship. If you look at the numbers themselves, most of the time there's consistently around a 2-year gap between the average ages, between the genders and things like that. There are a few kind of exceptions where over here, men's average age of first marriage is around 26, and women's average age of first marriage is around 22. But by and large, there's kind of a 2-year gap. Right? Here it's around 28 and it's around 26. Here it's around 24 for the men and around 22 for the women. That's kind of what we're seeing here. Okay, here's a different plot. These are two different scatter plots. And here I'm looking at, okay, let's look at what year in history, okay? So again, the data starts around 1890, and 1890, 1900, 1910, 1920, 1930, 1940, they measured data in about 10-year intervals. And then starting around 1940-something, they started taking measurements every single year, okay? And what we see is that from around 1890 to around 1960, there's a downward trend. People in 1890, men's average age of first marriage is around 26, okay? And from 1890 to around 1960, men's average age of first marriage keeps going down. Similar kind of thing for women. In 1890, women's average age of first marriage is around 22, and then consistently over time, that kind of seems to be dropping until around 1960. And then after 1960, men's average age of first marriage kind of steadily gets higher and higher as time goes on. And we see a similar kind of phenomenon for women as well, as after 1960, women's average age of first marriage kind of gets higher and higher and higher. This is I think this is kind of interesting to see, right? And so in these plots, there's a very strong relationship, okay? However, we cannot summarize these relationships with a single straight line, okay? This plot over here, single straight line would kind of do the trick. Overall, we can draw a straight line from this corner to this corner, and that would summarize the data very well, okay? Over here, there's definitely a relationship, but a single straight line would not work. Maybe we could divide the data in half, and we could say pre-1960, here's a straight line, and then after 1960, here's another straight line, okay? And I think that could work. But as far as the overall data set in its entirety, we cannot use a single straight line. We'd have to kind of split it at, say, like 1960, and then we would say, okay, now we can use a straight line kind of to project this, right? That's what we have there, okay? So what we're going to be looking at is, how do we describe these kinds of relationships? And first, we're going to just use like loose terminology, and then we'll quantify this, okay? So when it comes to, let me give you your first view quiz answer, which today is the letter E. E as in elephant is our first view quiz answer for week 8, Friday. Okay. So we want to be able to describe things like the shape, and then the trend, strength, outliers, things like that, okay? Overall, the shape, right now we'll just call them linear versus nonlinear. I took these pictures out of a textbook. That's why they look quite different from like ggplot or something. So, linear means the relationship can be summarized with a single straight line. Nonlinear is anything where a single straight line is not going to do the trick. Again, in a future course, you might describe nonlinear relationships in more specific terms, like you might say this is a polynomial relationship, or cubic, or exponential or logarithmic, or things like that. And there are ways to kind of describe these nonlinear things. Right now, we'll say linear for straight line. Anything that's not a straight line will be nonlinear. The direction, we can say the direction of the relationship is positive or negative, or neither positive nor negative, okay? Positive means, so again, when we're talking, this is for linear relationships. So if it looks like a single straight line, well, I guess we could have nonlinear, I don't know. Okay, but overall, positive would be large x goes with large y, and small x goes with small y. Negative is kind of, it flips around. Large x goes with small y, and small x goes with large y. So they kind of work in opposite directions. And then neither positive nor negative would be, no real trend can be assigned in terms of the direction. Large values of x aren't necessarily going with large or small values of y. Small values of x aren't necessarily going with large or small values of y. Let's take a look at a couple examples. So here, there's a bit of some outliers and some scatter, but overall we have a positive relationship. Here we're looking at the age of the vehicle, age of a car in years, and what's its odometer reading, okay? And what we see is, in general, older cars have more mileage driven on it, all right? So overall, we have a positive relationship. If you have a large X, okay, large value for age, you have a higher number of miles driven. Smaller value for age, fewer miles driven on it, okay? Of course, exceptions, but that's the general trend. Here's a negative relationship, okay? Large values of X have smaller values of Y. Smaller values of X have larger values of Y. This was, I think, looking at several countries over the course of at different points in time, and what we see is that when countries that had high literacy rate, this is a measure of fertility, total births per woman, is we see a negative trend. In countries that have higher literacy rate, there tend to be fewer total births per woman. Countries with lower literacy rate tend to have higher total births per woman. We have to be really careful when you see correlations and things like that. You have to be careful about assigning cause and effect, right? So sometimes we want to kind of jump to a conclusion and say, okay, when people learn how to read, then they're less likely to have babies or something like that. And it's not necessarily that one thing is causing the other, or that the reverse would be silly too. Like if somebody has a baby, they're less likely to learn how to read or something. That would be a silly kind of conclusion to draw. And a lot of times when you see some kind of relationship, there's often some kind of something complex going on. Higher education, the education of women in the population is associated with a decrease in infertility, and there's kind of complex things going on there. But related is kind of the role that women play in that particular society, or things like that. So anyway, this is just kind of an example here, and so one thing I want you to be careful about, and this is I do get I don't know what the right word is. Upset is not. I don't want to use too strong of a word like upset or angry, but in your final presentations, I want you to be careful about what kind of conclusions you're going to be drawing here, okay? If you start drawing cause and effect conclusions because you see some kind of relationship in the data, I might ask you a lot of questions about how you came to that conclusion. You can say, this is a trend we see. We speculate this might be the reason behind it. And here's some additional articles that kind of back up this reasoning that we're seeing. But we don't want to just say this thing is caused because of this other thing, all right? Because a lot of times that kind of thing that says this causes this can't generally be found in the data by itself. If you can find some kind of outside source that says this is causing this, and this is the relationship, this is the mechanism behind what's going on, I will accept that and support that. But if you just kind of say, all right, here's the trend that we see, and therefore we're going to jump to the conclusion that this is causing this, I might, I'll probably deduct some points about the appropriateness of these kinds of conclusions. Okay. All right. Here is an example of something that has neither a positive nor a negative trend. This is race times of different runners that competed in a marathon, and we have competitors of different ages, I think ranging from 18 to 70. And at this marathon, what we see is, there are people who are 40 years old that had very fast race times and slower race times. There are people age 50 who had faster race times and slow race times. People age 30 who have fast race times and slow race times. And so if we say, hey, is there a trend, if somebody is older, are they more likely to have a fast race time or slow race time? Or if someone's younger, are they more likely to have a fast race time or slow race time? We can't really make any kind of conclusion there, right? We're just going to say, well, yep, there's older people and there's younger people. There's fast race times and slow race times. And there's not really a strong kind of relationship between either of those things, okay? So that would be neither positive nor negative. Here's another example of something that is neither positive nor negative. This is some computer-generated data, but what we see is that large values of x go with large values of y. Small values of x all the way over here also go with large values of y. And then values of x in the middle go with smaller values of y. There is definitely a relationship. Okay, there's definitely a relationship between x and y, and it forms this U shape. But overall, can we, is there this trend of large x, large y, small x, small y, or small x, large y, or something like that? And overall, if we're limited to these terms, positive, negative, or neither, this falls under neither, okay? Again, for linear trends. Now, if we split the data in half at 0, then the right-hand side would be positive and the left-hand side would be negative. But overall, we can't really say positive nor negative. The strength of the relationship is kind of a measure of like how much scatter you see. Okay? If there's lots of scatter, your relationship's a little bit weaker, indicating that, if you had to make a prediction based on one variable, your prediction's probably not going to be very good. Okay? On the other hand, if you have very little scatter, you have a strong relationship, and if you were trying to make a prediction based on one variable, your predictions would be better. Right? So here is the y variable here is weight, someone's weight, and the x variable is, one is height, and on the right hand side we have waist size. Okay, so if you know someone's height, can you predict their weight? All right, and overall there's a positive relationship. Taller people tend to weigh more, shorter people tend to weigh less. Okay, but we have some tall people who weigh a lot, tall people who weigh less. Okay, we have some short people who weigh a lot and short people who weigh less. All right, so there's quite a bit of scatter. If you measure someone's waist size, that turns out to be a better predictor for weight. Okay, there's still some scatter here, but people with larger waists tend to weigh more. People with smaller waists tend to weigh less. And if you look at people who, looking at the height, if you look at people who are 70 inches tall, that person's weight can be anywhere from 120 to maybe 260 pounds, okay? If we look at waist size, and we look at people with waist size of 35 inches, okay, their weights could be anywhere from maybe 150, 160 up to 220, okay? So there's some scatter, but less scatter. And we would say waist size is a better predictor of weight than height, okay? And so we would say this is a stronger relationship, and this is less strong or weaker. So if we revisit this plot of age of first marriage for men and age of first marriage for women, we would say, okay, the shape is linear. Overall straight line would do the trick. The relationship is positive, okay? And we would say there's a very strong association because, if you look at years where average age of men's first marriage is around 27, there's very little scatter. It might go from 24.8 to 25.2, but kind of this very, very tight range of values for why we don't have a whole bunch of different values here. So very little kind of scatter. We'd say there's a very strong relationship there. Just a note, we always want to use kind of slightly loose terminology here, like words like tends to, okay? And that's because, individuals, there's always going to be some individuals in your data that don't necessarily follow the trend, okay? And if there's anything unusual, anything that kind of stands out, you probably want to investigate those and look at, is this value actually real, right? So if we saw, some data out here or data down here, we would want to investigate those in our data. We'd want to actually look up those rows in your table and just see, hey, what's going on? Why is this particular data point not fitting the overall trend? Okay, and maybe it's a mistake. Maybe it's a typo. Okay, maybe something went wrong in the data entry, or maybe it's reflective. In your past homework, you were looking at the relationship between the width and length of the diamonds. Okay. And, in general, these diamonds had a very strong correlation between the X and Y values, but there were some values that kind of stood out, some values that didn't quite fit the trend. And I think it's reasonable to kind of question those and say, are these real measurements or are these mistakes? Okay. And probably in a lot of those cases, I would guess that they were mistakes, but I don't know. But anyway, that's what we want to do. Okay, let me give you your second view quiz answer. Second view quiz answer today is the letter C. C as in cat. C as in cat. Okay, we might run out of time to cover all of the slides today, so we might have to look at some of this next week. So we measure the linear relationships using something called the correlation. So correlation coefficient is a numeric summary that describes the relationship between X and Y in our data. So rather than just saying strong relationship and weak relationship, we can use the correlation. Correlation is going to give us a number between +1 and -1. Never higher than +1, never more negative than -1. If you get a value close to +1 or close to -1, that's going to be a strong relationship. So if you have something like 0.9, that's a strong relationship. -0.9 is also a strong relationship, but in the negative direction. Okay, so the sign of R is the direction. Okay, values close to 0, and really I would say close to 0 is like anything less than 0.3. Okay, so going from -0.3 to +0.3, these are going to be weak relationships. Weak relationships. So if you have no scatter, the dots are in a perfect straight line, R is going to be 1 if it's positive, or -1 if you have something in the negative direction. Okay. So here's just some illustrative examples of different correlations. So this one has a little bit more scatter, so we have R of something around 0.72. Here is even more scatter, R of 0.48, still a positive relationship. And here we'd say, yeah, not hardly any kind of relationship. I guess overall still a little bit positive, but R is 0.19, which is pretty low here. Okay. How do we go about calculating correlation? There is a formula. We're not going to bother learning that formula by hand. Okay. Normally we just go to the computer and we just say, give me the correlation. Okay. And so you have your data, and you can pull a column, okay, or you can designate a column using the $ notation. So here, if I want to take the column for men's age of first marriage and column for women's age of first marriage, I would do marriage $men, because marriage is the name of my data frame, men is the name of the column, okay, and I would do marriage $women, marriage being the data frame and women being the name of the column. And I would put, do core. Core is correlation between these two things. And I get 0.985. So a very, very strong relationship between the age, men's age of first marriage and women's age of first marriage. Okay. A couple things to note about correlation is changing the order of your variables doesn't affect R. So correlation between x and y is the same as the correlation between y and x. All right, so flipping the order around doesn't change it. Changing your unit size will not affect r. So if you multiply by a positive constant, or you add some kind of unit, some kind of value, so like converting from Fahrenheit to Celsius involves doing multiplication and adding a constant or subtracting a thing, right? To go from Fahrenheit to Celsius, you subtract 32 and multiply by 9/5 or something. To convert from inches to centimeters, you multiply by 2.54. Doing any of these things is not going to change correlation. It will change the slope. Later on, we'll learn how to do linear regression, and it will affect the slope when you change units, but the correlation is unaffected. So correlation and slope are actually, correlation doesn't tell us anything about slope. Okay. Correlation itself is unitless, and the interpretation of correlation is only useful when you have a linear relationship. Okay. Correlation is just the result of a formula, and so you can throw data that is nonlinear, right? And you throw it into the formula and it spits out a number, okay? But that number doesn't have a very meaningful interpretation if it's not a linear relationship, okay? I wrote slide 18. This is wrong because the number of the slide is different, okay? I'm gonna run out of time. How many view quiz answers did I give you? 2. Okay, let me go ahead and give you your last one. Last one is B. B as in bear. B as in bear. We're gonna look at simple linear regression. Linear regression allows us to kind of draw a straight line. How do we draw that straight line? Okay, and that straight line we draw is useful for kind of making predictions. It's also useful for helping us understand the relationship between x and y. And you get this equation, right? It's going to be an intercept plus slope times x. Okay, our intercept we'll call a, and our slope we'll call b. If you pick up another textbook, they might call this beta 0 for a, beta 1 for b. I don't know, you might, I think in algebra 1 you had m for the slope and what was it, mx plus b or something. Okay, b for the intercept, so sorry, we're using different letters here. But you have an intercept and then you have a slope term, okay? If you pick up another textbook or you go online and you type in like, how do I do linear regression? There's always going to be talking about the y variable and the x variable, but they have all kinds of names for all of these things. So these are some of the names you'll see for the x variable. You got explanatory variable, predictor variable, input variable, independent variable. For y, we have response, predicted, outcome, dependent variable. I don't know, all kinds of different stuff. I don't know why we don't have agreement on all of these terms, but that's just a heads up, right? You go online and you search for like, I imagine you are using the internet to help you do stuff for your projects, right? And you come across different tutorials, you come across different things. You're going to see different language there. Okay. Here's an example of a linear regression equation that we might get, right? So I don't know when this data was taken. Obviously not now, because if you try to buy a used car, it's like crazy expensive. It's like, oh my gosh, why is this car so expensive? But here we're going to say this is the data that they collected, and then they say, okay, let's predict the value of the car based on how old the car is, right? And so, this is a new car. This is like your, 2023, Honda Civic or something. And then a 10-year-old car would be a 2013. A 15-year-old car would be a 2008 vehicle or something like that. And what we see is just, overall negative trend. And if we were to predict the value of the car, we might say, okay, a new car is 21,375. And then for each additional year, in terms of its age, our predicted value drops by $1,215, okay? Again, this must have been like data from a decade ago or something, okay? So if we had a 12-year-old vehicle, okay, we would plug in 12, and we would do 21,375 minus 1215 times 12, and we would get 67.95. We would predict a 12-year-old vehicle to be around $6,795. Okay, just a prediction. Actual value, obviously higher or lower than that. Okay. Oh, you can't see these dots. There are dots. Tiny little dots here. Okay. Here, I just wanted to demonstrate how we would do linear regression for a very small data set. All right, so this is a very silly example. I've got 6 people in my data, and don't do this, but we're gonna say, all right, why don't you tell me your weight, and I will predict how tall you are. Okay, so this is a bad party trick. But this is what we're going to pretend to do. Okay, we're going to say we've got these x variables, we got these y variables. Here, our x is going to be weight, our y is going to be the height. Okay, and we're going to say, okay, here's we gathered some information, and we say, okay, here's a person who weighs 104 pounds, and they're 61 inches tall, 5'1". Okay, here's a person that weighs 160 pounds, and they are 5'8". Okay, and so this is our data. It's a very small data set, so our line that we're going to make is not going to be very good or anything like that. But what I need to do is I need to do size equals like 3 or something. I'll put that in the notes here. Okay, but we're going to try to fit some kind of relationship there. Okay, well the command to make a regression equation in R is simple. We use something called LM. LM stands for linear model. We're trying to model this relationship using a line. And here we're going to do height tilde weight. Okay? So it feels a little bit funny, but we're going to say predict height, and the tilde is kind of like based on weight. Okay? So if we wanted to do the opposite, if we wanted to say, okay, you tell me how tall you are, and I'm going to predict your weight, okay, then we would do weight tilde height, right? So the one you're trying to predict comes before the tilde. The one that you're using to make the prediction comes after the tilde. Okay, so we're trying to predict the variable height based on the variable weight, height tilde weight. So we're going to do LM formula equals height tilde weight, or you don't even have to write formula equals, you just do LM height tilde weight, and then you do comma data equals the name of your data frame. Okay, so if we were dealing with the penguins data set, we would do and we want, I don't know, what would we predict body mass based on flipper length or something. We would do LM body mass underscore G tilde flipper length or something, I don't know, whatever, right? Comma data equals penguins, okay, to say this is our data is coming from the penguins data set. And then it comes back and it says this is your intercept, 52.39726, and your weight, the slope for the weight variable is 0.08595, okay? And so this says if we had to predict someone's height, we're going to take this number plus this times their weight. Okay? And so here I've added that regression line to the thing. You're already familiar with how to do this. We've seen this before, right? You have ggplot and then you add a geom smooth. And to say I want a linear one, we use method equals LM. And then it adds these kind of in default, it adds these error bars to kind of say like, it takes into account that like there's uncertainty. And it says, okay, well, the true line could be anywhere from here and here, but just overall, if you just want to fit a little line there, you do SC equals false. Okay. So here's our regression equation, right? So when you get the results, it kind of tells you your intercept and the slope. And so we said, okay, for a person with a weight of 170 pounds, we would do 52.397 plus 0.08595 times 170, and it predicts a value of 67. Yeah, question?
Is there ever a time when you want to have the error bars in your regression?
Sure. I guess if you have different data sets, okay, and one, you have a lot of data, and so you're very confident in or like there's not a ton of scatter in your data, and you're very confident, you're going to end up having a very small error bar. And on the other hand, if you have like another data set with like less data or there's more variation.
So the error bar is like purely based on the amount of data you have. So
the error bar is based on the amount of data you have and the amount of variation within the data, right? So if you have something where, we're trying to predict someone's weight based on their height, or predict their height based on whatever it is, you're going to have like two people with the same height value, and they might have wildly different weights, right? But on the other hand, if we're like trying to predict someone's like index finger length based on their middle finger length, okay, you're probably going to see a very strong relationship, right? If you have two people with the same middle finger length, their index finger length will probably not like vary too much, right?
So if you have like a chart with like facets and showing a bunch of different variables plotted against one variable, and you have like the linear regression, would it be like worthwhile to keep the error bars on so that you see like the variation?
Yeah, so the error bars kind of gives you a sense of like, how confident am I in this line, right? And if you have a narrow error bar, you can be like, okay, this line's going to be pretty good, all right? On the other hand, if you have a huge error bar, it's like, okay, this is the line I have, but let's be real. I don't have much confidence in this line.
So the larger the R squared value, the thinner the.
Yes.
So that is a good thing to tell you.
It's basically just kind of like a, full disclosure. This is how good my line is. Okay. Yeah. Okay. Well, anyway, we plug in 170 and it says 67, and we can kind of, I don't know if you can kind of see this. If I plug in 170 here, this line is right at like 67. Okay, and so that kind of lines up. You don't have to manually plug in 170 into the equation. Okay, you can have R do the work for you, and so here's the formula. So we have our model created. I have it saved. Okay, and then what you need to do is you need to create a data frame with the new values that you want to make predictions for. So here, if I want to say, I want to predict the person's height if they weigh 170 pounds. I want to predict the person's height if they weigh 180 pounds. I'm going to do data.frame, create a new data frame, and I create the column weight is equal to 170 and 180. And then I say predict using kind of my new values, and it says, okay, here's your prediction for 170, 67.00812, which aligns with what we got over here, 67.0085, I think some rounding discrepancies there. And then, here's our prediction for somebody who weighs 180 pounds, 67.867, okay? Okay, I've run out of time. We'll discuss some more next week. You have a holiday on Monday, so have a great weekend. I hope your projects are coming along well. Again, don't hesitate to stop by office hours, and I'm happy to help out. So have a great weekend. We'll see you next week.